All right, let's get started. Real quick, just so everybody's aware, you all have a homework due today. I'm collecting them up here, so if you have not turned that in, make sure you turn that in before the end of class. You have a homework assigned. It was actually assigned on Monday. Blackboard automatically just sort of turned it on for you. It's due on next Friday. Next week, we'll sort of reevaluate where we're at. I don't think we'll need to push this deadline back on this homework. I still think we can cover what you need to do to be able to attack this assignment. As long as you can do gross and net area calcs and then compute shear lag factors, you should be good. So that's what we're going to do today, is start with gross and net area calcs. As for the steel manual, you do need to start bringing it on a regular basis because we're going to start using it. I mean, we're actually going to be using it today. So you'll definitely want to have that with you. And with that, are there any questions? Because I'm going to just jump right into it. All right. So I'm going to start here because I think this is a pretty reasonable place to sort of pick back up, because I know it's been a little while since we've met. So remember, what we're doing now is we're starting to look at a tension member and discuss its pertinent limit states. So we have a tension member here. We have a wide flange that's being subjected to tension. So we're yanking on it, and we're trying to determine what are the states at which we determine that this element has experienced failure. So first off, we defined yielding in the gross section. So the gross section is the main body of the member, the sections that are away from the connection. And basically, once those sections hit a stress equal to Fy, we determine that the section has failed. Okay, and so for that, ultimately we'll compute like a phi-pn, like a factored resistance. We'll do the same thing for a couple other limit states, and then the lowest one is what's going to determine what the maximum capacity is. But we'll take it one step at a time. So in order to compute the capacity of a section according to gross section yielding, to get the nominal capacity, we take the yield stress and multiply it by the gross area. So remember, yield stress is something that you can just look up in that table 2-4. That's pretty easy. Gross area and net area we're going to talk about here soon. And then our phi value for gross section yielding is 0.9. As for our second limit state that we're considering right now, which is net section fracture, we need to understand two things. We need to understand what the net area is and what this concept of shear lag is. The reason why is because in order to compute the capacity of a section according to fracture in the net section, we need Fu, which is the ultimate tensile stress. Again, that's just a lookup. You just go to table 2-4 and there you go. And then we also need the effective net area. And the effective net area is just the net area times an adjustment factor for shear lag. Now the phi value for net section fracture is a little lower because if a member yields, it just gets longer. But if a member fractures, it is separated in half, and so that's a little bit of a bigger deal. So our resistance factor is lowered accordingly. So just so everybody's aware, I want everybody to understand the difference between nominal capacity and design capacity. So nominal capacity is just our mechanical capacity, and then the design capacity is adjusted by phi. And then again, effective net area is net area times the shear lag factor. We're going to skip shear lag for now. We'll talk about that later. But right now, I want to get into gross and net area. Don't forget about block shear. Block shear will be a little bit down the line. Okay. Let's talk about gross and net area. So in general, for bolted connections, the way that you compute the net area is you take the gross area and you subtract the area lost due to bolt holes. And I'll explain what that means through a couple of examples. Now, I want to make sure everybody's clear on terminology. If you hear me use the term a line of bolts, lines of bolts run parallel to stress, okay? Parallel to applied load. So I'm yanking on this member like this. This section would then have two lines of bolts in each flange. Does everybody see that? So here we have a flange, we have a line here, and a line here, line here, line here. So each line has 5 bolts, okay? Everybody okay with that? I just want to make sure everybody's clear on terminology. So if I start using the term line of bolts, that we all understand what I'm referring to. Sound good? Now let's talk about the area lost due to bolt holes for a second. Now what we're going to do for tension members is this, okay? In order to determine the diameter of a bolt hole, what we're going to do is we're going to take the diameter of the bolt and we're going to add 1/8 of an inch, okay? Now there are two reasons for that, and the first is this, okay? How many of you have ever done any sort of mechanical work, fixed a car, fixed a lawnmower, anything like that? Has anybody done any work at all in a garage in your life? Okay. You're engineers. If I had a bunch of engineering students and nobody raised their hand, I go, have you taken apart a remote or something? Well, one of the things that you will find is that if you actually, so let's say you have a bolt that is 1/2 inches in diameter, and you try and insert that into a hole, a steel hole that is drilled exactly 1/2 inches in diameter, it doesn't work. The bolt hole actually physically must be drilled a little bit larger for the purposes of erecting the structure, or the car, the lawnmower, whatever you're working on. So why do we add 1/8 of an inch? Well, we don't really add 1/8 of an inch, we add 2/16. The first 1/16 is for erection tolerance, and basically what I'm saying here, what that means is the actual hole is physically larger than the diameter of the bolt. And for standard holes in structural steel, that standard increase is 1/16 of an inch, okay? That can change a little bit if you've got some really, really big bolts, but we're not really going to be dealing with that in most common steel design applications. So we add 1/8 of an inch because we're adding 2/16. So we add 1/16 for erection tolerance. Why do we add the other 16th? Well, we add the other 16th for what's called damaged material, okay? So, excuse me. So what's going on with damaged material? Well, if you're using, like, let's say a mag drill to drill a steel hole, how many of you have ever done any work drilling with steel or done any sort of work? I know some of you here recently went down to the DOH and they showed you some welding and whatnot. Well, if you ever do any of this work, you'll find that, when you're drilling, inside steel, you get all these ribbon cuttings that are all over the place. And if you actually look at the hole, it's a lot of times it's not this nice, pretty little cylindrical, smooth surface. It can be kind of rough. It can be kind of jagged. It can be kind of gnarly. So what we do is we add another 1/16 of an inch to account for this little lip of material being damaged. And that's not to say it's not entirely useful, but what we're saying is, can you really count on this little lip of material being effective in transferring load to the entire member? And so for tension member limit states, we say no. Okay? So is everybody okay with that? So now here's one thing I'm going to tell you, and it's not really going to affect us right now, but y'all are going to get ticked off at me later when we look at bolted connections. When we look at bolted connection limit states, we are actually looking at the physical properties of the hole. So later on, when we look at bolted connections, we won't add 1/8 of an inch, we'll add 1/16 because we're actually looking at this physical layout of the hole. So for now, it's 1/8 of an inch, but when we get to bolted connections, it'll be 1/16. Everybody okay with this? All right. If you're okay with that, let's get some math done. So I've got a plate, and I want to compute the net area of this plate shown. Now I've got a plate. It's got 8 bolts in it. It has 3/4 inches diameter bolts are being utilized, and I want to compute the net area. Now, just so everybody's aware from a strategic standpoint, what do you think the first step in computing the net area is going to be? Calculate, whole, but what am I? The gross area. There we go. So what we're going to do is we're going to calculate the gross area, and then we're going to calculate the net area accordingly. So, hold on. So here's the problem. So what we're looking at, we're really looking at this plate right here, this plate 8 by 3/8. So if you want to sort of just look at the 8 by 3/8 inch plate, what we're looking at is something like this. We have a plate that is like this, and we've got 1, 2, 3, 4, 5, 6, 7, 8. And then that plate, you can imagine it's sort of going on forever this way, and it's being yanked on with some load. Okay? So a pretty basic calc, the plate is 8 inches wide, 3/8 inches thick. So what's the gross area of the plate? What's that? I mean, anybody? I know it's cold, but it ain't that cold. The plate is 8 inches wide. It's 3/8 inches thick. So what's the area? There we go. And how'd you get that? There we go. It's pretty straightforward. So gross area. So AG is 8 inches, 3/8 of an inch, 3 square inches. Not too bad, right? All right. Let's look at the hole diameter, okay? Now, we know what the bolt diameter on this problem is, right? What is that? Say it again. 3/4 inch. Okay. Now, what therefore is going to be the hole diameter? It's going to be the bolt diameter plus what? 1/8. And so that's going to be what? What's 3/4 plus an 8? 7/8. There we go. Now, now right off the bat, let me ask you this. Ultimately, what we're going to do is we're going to take the gross area and we're going to subtract the area lost due to bolt holes. So let's just think about this in terms of the number of bolt holes. How many bolt holes do you think we should subtract from this section? What's that? So you saying what? 8? You saying 16? Any other guesses? I'll give you a hint. Remember, what's our secret weapon of structural engineering? It's a samurai sword or lightsaber if you happen to be a sci-fi fan. So remember, we're talking about the gross and the net section. We're cutting a section through this plate. Remember, we're yanking on the plate like this. So samurai sword or lightsaber. How many bolts are we cutting through? 2. We're cutting through 2. We're using 8, but remember the cross section looks like this. All right? So think in cross sections. Okay? So I guess the question is, what's the area of a bolt hole? So what is the area of a bolt hole? Somebody tell me. I'm just talking about the formula. What's the form? What are we going to use? Somebody else. Pi r squared, right? Sounds like a good answer, right? It's wrong, and I'll explain why. You've got to think in cross sections. Remember, the samurai sword or the lightsaber, if you're a sci-fi fan, what's that going to look like? What's that? Hold on. Give me a sec. Let me test my 3D art skills a bit. All right. So let's look at this plate in isometric. Let's look at it in 3 dimensions. So here's the plate, and it's going like this, right? And we're yanking on the plate like that. So what do the holes look like on the top? Well, the holes, they sort of look like this. We got a hole here, hole here, hole here, hole here. We're cutting through the holes. So on top of the plate, we're sort of cutting like that, like right through those holes, right? But remember, cross-section. So through the cross-section, what we're cutting through is this. So what is the area lost due to bolt hole? How do we calculate the net area? We take the gross area minus those. And so how do I calculate the area of one of these? The diameter times the thickness. And that's how you compute the net area. So therefore, I propose that the net area we take the gross area and we subtract, for this problem, 2 times the hole diameter times the thickness. Okay? So that's going to be 3 square inches minus 2 times 7/8 of an inch times 3/8 of an inch. And so what does that come out to be? We'll say in, excuse me, in 2 decimal places. We'll say it again? 2.34. Do I have a second on that? What do you think? Didn't expect that. Area of a hole wrong. Okay, I got you and then you. You go ahead. I'd just go with the decimal because, and you're going to see why here in a second. Yes. No, no. But I don't want to do a spoiler alert, but, or do a spoiler, well, it is spoiler. It's not 4. It's not 3 either. And we'll get there. But I see what you're saying, but the exact question that you're talking about, we answer in explicit detail later when we explicitly do block shear. Did anybody else have a question? I thought somebody else had a question. What? I think we have a glitch in the matrix. It's something with the screen because we in concrete design it was doing something similar as well, but my computer's fine, so I don't care about the screen in here. So you can read the screen, right? So that's all right. Any other questions? No, this is important stuff. All right, let's look at the next one. Okay, so the next one, now we're going to compute the net area of a rolled shape. Okay, so I got a rolled shape. It's a W10 by 49, and it's 3/4 inch diameter bolts. We're still going to keep the same bolt diameter, but we now have a different shape. Okay, so let me go to my little handy dandy notebook here. It's a clue. It's a clue. Couldn't help it. Yeah, if my voice wasn't, I could probably do it a little better, but okay. So now we have a rolled shape. We have a W10 by 49. So, but we're still going to, the process is going to be the same. In order to determine the net area, we need to determine the gross area. What is the gross area of a W10 by 49? Look it up. And so for those of you that I see that are just sort of sitting there because you're like, yeah, I know Dr. Mike said to bring the manual, and I know that I didn't, I'm going to go. Say it again. All right, hold on. Now, I see a lot of people asking, or what page is this on? What page is this on? Say it again. It's actually not a bad idea in your calculations, and I'm not going to get super intense with you on your homework assignments, but when you get out in the field and you're doing these calculations for real, put a reference. Page 1-28. Now, before we move on, I want to make sure everybody that's got their manual is able to find this. Well, what's the shape? It's a W10 by 49. So you're going to go in the W-shaped table, that's table 1-1, and look up the shape for a W10 by 49. Here, I'll write that here on the screen. Oh, okay. According to UPS. Y'all got it? I know. Hence why I'm doing this. Now, were you able to find it? The value? You good? Y'all good over here? Everybody good? What's that? All right. Is everybody good? Okay, all right. Now, don't change the channel too quickly. All right, so we have that. We have the hole diameter. Now remember, we have for this problem, the bolt diameter is still 3/4 of an inch. So therefore, the hole diameter is 7/8. All right. Now, for the net area, let's take a look at this section. How many holes are we going to subtract? 4. Is everybody okay with that? Samurai sword or lightsaber? Okay, so how do we compute the area of that hole? The diameter times the thickness. So what is the thickness? 0.56. Now, why are you using that one? I want to hear it. I'm getting what she was saying, that it's the flange, that you're using T sub F. And you're using 0.56 because that's the decimal value, not the drafting value. We don't use the fractional values for design computations. So what we'll need for net area is we'll need 0.56 inches, again from that same table. So is everybody able to find that value? Remember, don't use the fractional value, use the decimal one. Sound good? All right. So therefore, the net area is the gross area minus 4 bolt holes. And so what does that come out to be? We'll say it at 2 decimal places just to keep it simple. 12.44. Do I have a second on that? All right. All right. Not too bad, right? Are there any questions about that? Okay. So, would you agree that up until now, the expression for net area that we have computed or derived is as follows? That the net area equals the gross area minus the sum of the diameters of the holes times the thickness, right? Whatever thickness, is appropriate. If it's a web thickness, a flange thickness, whatever. For now, is everybody okay with that? Okay. This is where I want you to pay attention. So this is for the next maybe 5 minutes. This is movie time. Okay. This formula by itself only works for a pattern like this. Okay. And so a rectangular grid-like, pattern of bolt arrangements. And so I'd say more often than not that's going to be the case. However, sometimes it makes sense to arrange your bolt pattern like this, okay, to stagger it, okay. Now, first off, golden rule of engineering is to try and keep it simple, so why the hell make it more complicated? Why arrange bolts in weird patterns like this? Well, the short answer is to increase the net area. See, if you can stagger your bolts, you can increase the path along which a fracture must occur, and you can increase the net area. So you can increase the capacity of your member without making it thicker, without making it more expensive. So it's a trick to to making it to making your design economical. Now, one of the complications is that you have multiple failure paths that need to be investigated. Now, all these paths have to be investigated on what's called the lead line. Okay, and I'm going to explain what the lead line is here in a second. So first off, what do I mean by possible failure paths? Well, if I'm yanking on a section, this might be a possible failure path. That might be a possible failure path. That might be a possible failure path. So first off, how do you identify possible failure paths, and how do you account for them appropriately? So first off, to handle staggered bolt paths, we introduce what's called a stagger factor. Okay? Now, a stagger factor is computed as follows. It's S squared over 4G times the thickness. Now, the way that this works is anytime we encounter a single diagonal path from one bolt to another, we add a stagger factor. Now, this stagger factor has been derived for a long time. It's been in specs since something like the 20s or the 30s, and it's certainly not going anywhere anytime soon. See, the facts are the actual stresses and the math in order to determine the stresses in a bolted connection are really, really complicated. And for years, this has served as a really reasonable way of accounting for that increase in capacity in a very simple fashion. So we're not getting rid of stagger factors anytime soon, okay? So just so everybody is aware in terms of the math, or in terms of the symbols, there's two distances that you need. There's S and there's G. S is the longitudinal spacing, and that's parallel to the load, and then transverse spacing is perpendicular to the load. And what you do is you add a stagger factor for every diagonal path that you see. So for instance, this possible failure path, you would not add any stagger factors at all. This one, you would add one stagger factor. This one, you would add two. Okay? Is everybody okay with that? So you add one for every diagonal path from one bolt to another. Okay? So S, G, and then the thickness. If you actually open up the code only specifies the S squared over 4G, but the code states, that's just for the path. You have to multiply times the thickness to get the area, hence why the thickness is included here. Okay? So far, so good? Now let's talk about the lead line. we only consider bolts along the lead line. Now the lead line is the path that leaves all of the bolts intact at the end of the day, okay? And so reason why is we'll consider bolted connection failure later. So here we're just looking at the tension member, okay? And so the way that that works is this. This is the easiest way that I can explain it. Imagine that in your hands you have a piece like a big rubber band, okay? And so here's the tension member. The tension member is going, along the room, and then the connection at the end is right here, okay? Imagine taking that rubber band and stretching it. All the bolts that it hits, that's the lead line, okay? That's the easiest way to explain it, but another way of explaining it, which is quite visual, is right here. So I'm going to ask you a question. Would this path fall along the lead line? Now I'm going to answer this one for you. I'm going to say the answer is yes. The reason why is if that plate fractures along that line, the bolts remain intact, okay? So all the bolts are still in one piece. So I answered this one for you. How about this one? Would this path fall along the lead line? Yes, it would, because the bolts remain intact. What about this one? Yes, all the bolts remain intact. What about this one? No. Now you can see it, right? Because if you fail that band, that front bolt has sheared off, okay? And so the reason why we don't consider that path is because this path is not seeing the full amount of load. It's only seeing, 6/7 of the load, because this bolt has already taken off some of that stress. So we only consider bolts along the lead line because they're the only paths that are seeing 100% of the load. Any questions? No, because the main body of the member is here. So all of this is seeing 100% of the load. So really, this isn't seeing any load. So yeah, that's why it's almost like you start at your brake line and go that way. Start at your brake line and go into the connection. All right. Any questions? Okay. So I propose that we now have a more refined expression for net area, and it is this. The net area equals the gross area minus the area lost due to the presence of bolt holes plus the addition of any necessary stagger factors in order to account for diagonal bolt paths. Excuse me. Now, if you don't have any staggered paths, or if you just have a rectangular grid arrangement, then all your stagger factors are 0, and that corresponds to the same equation that we derived before. So I think this is a pretty reasonable expression. Also, one thing to keep in mind, everything that we've been talking about right now is for bolted connections, where you're actually removing material from the section in order to generate a connection. Well, what if you're doing a welded connection, where all you're doing is just tacking and placing a fillet weld? Well, you're not drilling, you're not punching or reaming or using a CNC to cut material away from the section. It's the same section. So in general, especially if you're looking at fillet welds, for welded connections, the net area equals the gross area. So there's no, computation that you have to perform. Okay? So we'll look at welded connections later, but the tension member calculation is usually pretty easy. All right. Any questions? All right, so I got a problem for you. Let's calculate the net area of this plate. Okay, so I'll give you a second to draw this one out. I have a 3/4 inch diameter bolts. I'm keeping it simple on the bolt diameters because I don't want to get super confused here in class. I think I have one example here recently where the bolt diameters changed, but by and large it is what it is. But I'll give you a sec to draw that out. I have it pre-drawn out on my notebook, but I think you'll find this is pretty straightforward. sec. Can you still read this one? Okay. Everybody good? Okay, now the dimensions of the plate are right here. They are 12 inches, excuse me, the plate is 12 inches wide and it's 1 inch thick. So right off the bat, we can go ahead and compute, using my green pen here. Right off the bat, we can go ahead and compute a gross area. So the gross area is 12 times 1, which is 12 square inches. The bolt holes, so we have a bolt diameter of 3/4 of an inch. So what's the hole diameter? There we go. Okay. Now, one of the things I'm going to go ahead and do right now is compute a stagger factor. Now remember, the formula for a stagger factor is S squared T over 4G. So I want you to help me out. Let's look at this connection. Now the thickness, that's simple. The T is 1 inch. That's easy. What about the stagger? What value here on this connection is going to be the stagger, the S value? 1.5. Remember, along the direction of stress, we are yanking on this member this way. Okay? So the 1.5 goes that way. That's the S value. So this is 1.5. What about the gauge distance? What's that going to be? 3.5. There we go. So therefore, our stagger factor is 1.5 inches squared, don't forget to square it, times 1 inch over 4 times 3.5 inches. And so what does that come out to be? 161. There we go. You're exactly right. Just remember, I'm allowed 7 mistakes, so we'll call that about like 0.02. Notice how it never quite gets to 7. I'm an engineer. I use factors of safety. That was a good one, actually. That actually was pretty good. All right.
Yeah, that's a mistake.
It should, but... All right. Okay, so I'm going to sort of redraw the connection down here just because it's a little dark here on the screen. You all don't necessarily have to do that. And I'm also not drawing it to really any significant scale. I'm just sort of redrawing the bolt pattern. So we have that, we have that, that. Something about like that. Okay. Now, really for the sake of discussion, the lead line is sort of are we talking about the lead line? Are we talking about this, on this end, or are we talking about this end, left or right? Left. Okay. So really I'm focused on those 3 bolts there on the left. Okay, I'm going to throw some letters on here. This is pretty common in steel design, just to make sure that we're all speaking the same language. So what we'll do is we'll say this is A, this is B. I'm talking about the A and B, I'm talking about on the edge of the plate. We'll say this is C, this is D, this is E, and we'll say this is F, and this is G. Stay. Trust me. Trust me. Trust me. They're good now? Okay. All right. The reason why we're doing this is because I want to be able to name our potential failure paths so that we're all speaking the same language. So, for instance, remember, when you're dealing with a staggered connection, there are multiple possible net areas. So we're going to compute all of them. So let's start listing possible failure paths. Now I will start. One of them I'm going to say is A, D, F. Okay? And so that path is this path right there. You tell me, is that a valid potential failure path? Does that fall along the lead line? All right. Now, you say, why are we doing this? Name me another one. B, C, D, E, G. Okay, that's one. Give me another one. B, C, D, F. Here, let me color that one in. So B, C, D, F. What about another one? Here we go. B, C, D, F. So B, C, D, F, and A, D, E, G. But what's the deal with those? Those two. They're basically the same, right? It's the same number of bolt holes, and it's the same number of staggered paths. So I'm going to sort of list those together. Okay? So, so B, C, D, F, and A, D, E, G. Sound good? Any questions? Well, let's look at each of these. All right. This is actually a good time to go ahead and do this. All right. What do you mean? Because you need to be able to identify all of them. Give me a second. What's that? You could do BCEG, but what would be the problem with BCEG? You wouldn't be along the lead line. So the short answer is no. Look, here's what I'm getting at. Each one of these paths is going to have a different net area. We have to determine which one governs. Okay? The reason for the naming is so that we can all name failure paths and we're all speaking the same language. So I'm not saying that path over there and this path right down here and that path over yonder and then. Give me a second. All right. So let's just sort of summarize our math so far. We have a gross area of, what was it, 12 square inches? we have a stagger factor of 0.161. And then we have a, what is it? Well, we know the thickness of the plate, and what's the thickness of the plate? 1 inch. And we know the whole diameter is 0.875. So why don't we just say that the area of a given hole is 0.875 square inches. Is everybody okay with that? So in general, how do you, bless you, in general, how do you compute a net area? You take a gross area minus the sum of your holes plus the sum of all your stagger factors. So here's what I'm getting at. Here's what I'm getting at. I'm going to draw a little table down here. So let's take the first path. A, D, F. Okay? How many holes are going through path ADF? How many bolt holes? 1. How many stagger factors? Why 0? Because there's no diagonal path, right? So can anybody tell me what the net area of that path would be? Like, how would you compute the net area of this path? Like, what would you do? You'd take the gross area minus, minus how many of these? Plus how many of these? And so what is that? So we'll say 11.13. All right. Now what's the next one? B, C, D, E, G. How many holes are through path B, C, D, E, G? 3. How many stagger factors? 2. And so, what does this come out to be? Say it again. 9.70. Do I have a second on that?
Would ACDF be with that?
Well, I see what you're saying with ACDF, but from a physics standpoint, path of least resistance, why would the steel fracture this way from here to here when it could just fracture from there to there? All right, and then the last one. Now, this is why I grouped these two together. So we have B, C, D, F, and A, D, E, G. What, how many, let's take the first one. Let's just take B, C, D, F. B, C, D, F. How many bolt holes? How many stagger factors? All right, what about the other path, A, D, E, G? How many bolt holes? How many stagger factors? It's the same path, so it's just symmetric. So this is 2, and that's 1. And so what's that net area? 10.4. And so there you go. So what is the net area for this section? It's 9.7. Why is it the smallest? Well, if I'm yanking on this member, where is it going to fail? It's going to fail along the path of least resistance. And the path of least resistance is the path that has the less area, or the least area, to resist that load. So the net area is going to be the smallest of these, not the largest. Bless you. So the net area is 9.7 inches squared. At the very least, you should be able to do your first homework assignment, or first problem on the second homework assignment. let me say one thing, and then we're going to call it. This problem was somewhat basic because the staggers and the dimensions were all symmetric. The next problem, that's not going to be the case because they're going to be different. So it's going to make the math a little more bookkeeping oriented. That's all I got, everybody. I will see you on Friday.